In this video, we're going to discuss some matrix operations. Previously, we introduced matrices in the context of solving linear equations, where we dealt with the augmented matrix in row echelon form. But we can also study matrices on their own. By better understanding matrices and what we can do with them, we'll also expand our understanding of systems of linear equations. So in this section, we're going to introduce the various operations that can be done with matrices. The first is called matrix addition. Right, so we're going to add two matrices together. So first of all, to add two matrices together, they should both be the same size, say m by n, and their sum is also the same size matrix, also m by n, and the way you add them is just by adding the corresponding entries of the two matrices. Okay, so in this example here, we're adding these two by 3 matrices, and again, you just add them the corresponding entries, right? So the result will be a 2 by 3 matrix. So the result will be a 2 by 3 matrix, and so the first entry is going to be -2 plus 1, and then going across 4 plus 2, and then 7 plus -5, and then 0 plus -1, and then 1 plus 3, and then -3 plus 1. And then you calculate the entries. So what do we get? So -1, and then 6, this is 2, this is -1, this is 4, and this is -2. And we see that the resulting matrix is the same size. This is also a 2 by 3 matrix. Okay, so matrix addition is fairly straightforward. You just add the corresponding entries in the same location. As we said before, when adding two matrices, they have to be the same size, right? So in this example here, where we have a 3 by 2 matrix on the left, but a 2 by 3 matrix on the right, they're not the same size because they have different numbers of rows and columns. So you're not able to add these two matrices together, and so it's undefined. Okay, so that's matrix addition. The next operation is called scalar multiplication. So the way scalar multiplication works is you take C, which is a scalar. So a scalar is just a number that's by itself. And then the scalar multiple is to take the scalar and multiply it with a matrix. And again, the resulting matrix is still the same size. The way you do the scalar multiplication is the scalar is multiplied by every single entry in the matrix. Right, so in this example here, when I write it out, so the scalar -4 is multiplied by each entry. So we have -4 times -2, and then -4 times 4, and then -4 times 7, and then so on, right? So -4 times 0, -4 times 1, -4 times -3. And then we just calculate the entries. Okay, so this is 8, this is -16, this is -28, this is 0, this is -4, and this is 12. And again, we see that the resulting matrix is the same size. Okay, so this is scalar multiplication. So again, the scalar just multiplies every single entry in the matrix. we're going to see in a little bit that multiplying two matrices together is somewhat complicated. Before we do that, we're going to discuss something called the dot product. So here we have something called a row vector, right? So it's basically just a matrix with a single row, and this is called a column vector. It's a matrix with a single column, and the dot product is going to take this row matrix and multiply it with this column matrix. So the way the dot product works is you multiply the corresponding entries together, right? So x1 times y1, then x2 times y2, and then x3 times y3, and so on, and then you add all of those together. So after calculating this dot product, so multiplying the corresponding entries and then adding them all together, the result should be a single number. So let's try to calculate the dot product with these two vectors with 4 entries, right? So this row vector with this column vector. Okay, so writing out the calculation, right? So again, we're multiplying the corresponding entries together. So -2 times 1, then -7 times 4, where you add it to the previous results. Then the next term is 0 times -5. Then the next term is 3 times -2. Right, so this is, the first term is -2, this is -28, this is 0, this is 6, minus 6. So again, we have to add them all together, right? So -2 minus 28 is -30, minus 6 is -36, and so we see that the result is a single number. Okay, so it doesn't matter what the length of the vectors are, the result of this dot product is always a single number. Okay, so the reason that we first discuss the dot product of these vectors is because matrix multiplication is just a bunch of these dot products calculated together. So let's discuss matrix multiplication, right? So the first thing to be aware of is that typically when you multiply two matrices, the two matrices could be different sizes, right? So A is going to be an m by n matrix, and B is going to be an n by p matrix. And the matrix product, say A times B is equal to C, results in an m by p matrix. So first let's talk about the sizes of these matrices, right? So n here is the number of columns for A, and the n here is the number of columns for B, the number of rows for B, right? So this n is the number of columns, and this is the number of rows for B. So the number of columns for A should match the number of rows for B, and the size of the resulting matrix, m by p, so the number of rows for C is the same as the number of rows for A, and the number of columns for C is the same thing as the number of columns for B. Okay, so so that's the sizes of these matrices, and then finally how you calculate the individual entries is, so the entry in the ith row jth column of the result is calculated as taking the dot product between row I in A and then row J in B. Okay, so we'll see in a second exactly how you how you take the individual rows in A and then the individual columns in B and multiply them together to get the entries in C. Okay, so let's take a look at some examples of matrix multiplication in action. Right, so the first thing you want to pay attention to is the sizes of the matrices that you're multiplying together. Right, so we see that A has 2 rows and 3 columns. Right, so A is a 2 by 3 matrix, and B is a 3 by 2 matrix. So the first thing we should check is that the number of columns of A matches with the number of rows of B, which it does. Right, so this is 3 and this is 3, so they're the same. And the other thing we want to notice is the number of rows in A and the number of columns in B. So that'll tell us what the size of the resulting matrix is. Right, so the result is a 2 by 2 matrix. Okay, so let's just preliminarily identify the entries, right? So let's call this C11, C12, C21, and C22 for the resulting matrix. Right, so this is the entry in the first row, first column, first row, second column, second row, first column, and then second row, second column. And so as we said before, each individual entry in the resulting matrix is calculated as a dot product. Right, so first entry, the entry in the first row, first column, C11, is calculated as taking the first row in A and the first column in B. So it's row 1 in A, dot product with column 1 in B. So this row with this column. And it's the dot product, right? So let's write it out. So you multiply the corresponding entries and then add them all together, right? So -2 times 1, and then plus 4 times 2, then plus 7 times -3, 7 times -5. Okay, so what do we get here? This is -2 plus 8 minus 35. So that's -37 plus 8, so that's 29. So the first entry here is 29. And then we continue with the other entries, right? So C12 is row 1 in A, dot product with column 2 in B. Right, so first row here, second column here. So writing it out, what do we get? So it's -2 times -1 plus 4 times 3 plus 7 times 1. And calculating it, that's 2 plus 12 plus 7. That's 21. So this entry is 21. And then we calculate the other entries, right? So C21. So that's row 2 in A, dot product with column 1 in B. So this row dot with this column. So writing out, that's 0 times 1 plus 1 times 2 minus 3 times -5. So that's 0 plus 2 plus 15, so that's 17. And then next is C22. So that's row 2 in A, dot with column 2 in B. So this row times this column, so that's 0 times -1 plus 1 times 3 minus 3 times 1. So what is this? This is 0 plus 3 minus 3, so that's equal to 0. Okay, so you calculate the entries of the resulting matrix one by one, just taking the dot product of rows on the left matrix with columns on the right matrix. Okay, so that's matrix multiplication. So below here we have some additional examples. Again, the first thing you should always do is to take note of the sizes, right? So this is, the one on the left is 3 by 1, on the one on the right is 1 by 3, right? So the one here matches with the one here, so we're okay. And then this is a 3, so this is a, and this is a 3, so the result is a 3 by 3 matrix. And okay, so calculating it, so what do we get, right? So first row here, first column here, that's -7 times 4. First row here, second column here, that's -7 times -1. And then first row here, third column here is -7 times 3. And then continuing the other entries, right? So now we go and move to the second row here. So we get -2 times 4 here, then -2 times -1 here, and then -2 times 3 here. And then third row, 6 times 4, 6 times -1, 6 times 3. So calculating this, right, so -28, then 7, then -21, -8, 2, -6, 24, -6, and 18. Okay. So this is what we get in example B. And then moving on to example C, on the left we have a 1 by 3 matrix, and on the right we have a 3 by 1 matrix. So basically a row column and a row vector and a column vector, right? So the resulting should be 1 by 1. This is basically just a dot product, right? So result is 1 by 1, or just a single number. And what is that? It's just the dot product, right? So 4 times -7 minus 1 times -2 plus 3 times 6. So what is this? This is -28 plus 2 plus 18. So that's equal to -8. Okay, so that's matrix multiplication, right? So again, look at the sizes of the two matrices, figure out what the size of the resulting matrix is, and then proceed to do the dot products of rows with columns. So one thing to be careful about with matrix multiplication is, in general, the what's on the left and what's on the right is important, even if the two matrices have the same size, and they're both square matrices, right? So matrix multiplication is not commutative. So you can see in this example that I have down here, on the left I have the matrix 1, 2, 3, 4, and on the right I have the matrix -2, 4, 7, -5. And then when you multiply these two matrices, this is the result. And then if you reverse the order, right? So here, let's call this A, and this is B. This is B, and then now A, right? So if you reverse the order, in general, the product does not give you the same result. So so matrix multiplication is not commutative. Okay, so going back to the calculation on this example on page 3, I see I've made a mistake in the first entry here, right? So when I took the dot product of this row with this column, right, so I wrote it out correctly here, and you get -2 plus 8 minus 35, right? So that's -37 plus 8, so that should be a -29, and so this entry should be a -29. Okay, so on this last page for section 2.1, we're going to tie together matrix multiplication with systems of linear equations. So suppose you have the following system of linear equations. So in this example, it's 3 equations in 3 variables, x1, x2, and x3, right? So with unknown coefficients and unknown constant terms. So the thing to pay attention to here is if we look at how the left side of this equation is written, right? So coefficient times variable plus coefficient times variable plus coefficient times variable. So how this is written out is just how a dot product is calculated, right? So it basically is the dot product of the coefficients with the variables x1, x2, x3. Right, so we can represent this thing as the dot product again of the coefficients with the 3 variables, and what you get is exactly this expression here. And you can say the same thing about the other equations, right? So the second equation is also the dot product with the corresponding coefficients with the variables x's, and the same thing for the third row, right? And so if you put together these individual dot products, you can translate it into the following matrix equation, right? Because again, the first equation is the dot product of this row with this column is equal to B1. And then the second equation is the dot product of this row with this column is equal to B2. And the third equation is the dot product of this row with this column is equal to B3. And so the system of linear equations can be written as this matrix equation here. So again, this example is 3 equations in 3 variables, but in general you can have any size system of equations in m equations in n variables, right? So typically in general this will be an m by n matrix, so it doesn't have to be square. This will be a column vector with n entries, right? So this is an n by 1 column vector. And then this will be an m by 1 column vector. Right, so the reason it has to be this case is because the matrix multiplication, right? So this number n has to be the same as this number, and then the resulting size should be this by this, right? So when you have mismatched number of equations with number of variables, you should be careful about the size of these matrices, right? So typically the coefficient matrix is called A. This is the vector x, and this is the constant vector b. And it's written as ax is equal to b. So a times x is equal to b. Okay, so now we have 3 equivalent ways to represent a system of equations, right? So for an system of equations like this, you can either set up the augmented matrix as we did in chapter 1, or also now represent it as a matrix equation a times x equals b, where a is the coefficient matrix, x is the vector of unknowns, and b is the vector of constant terms.